So good morning, everybody. This second lecture is going to be devoted to dynamical mean field theory. We've heard about it in several of both the school lectures and some of the conference talks already. So it's probably time that some brief introduction to it is actually given. So that's what I'll do in the first 25% of the lecture. And then the rest of the lecture will be devoted to describing a selection of quite recent advances using this technique. And since I don't like talking about things I don't know well, I picked these examples among work in which I have been involved. But of course, there's been a very, very large number of developments in this field, and many of the talks in the conference will actually describe other aspects of recent developments of DMFT and its extensions. And I just want to remind you that the third lecture on Monday will be devoted to a quite different topic, which is transport in cold atom systems. Okay, so in the general lecture yesterday, I emphasized that the sort of standard model of condensed matter physics, which is that we have a solid is a kind of electron gas, and the interactions complicate the problem in a somewhat painful way, is a view that has been extremely successful for many, many materials, but for strongly correlated electron materials, we really have to go beyond this sort of description. In those materials, we have to go back to atoms, and the challenge is to try to describe the whole, to bridge the energy scales from the high energy scale or short time scales in which excitations will be basically atomic-like to low energy or long time scales in which excitations will be in a metal, let's say, quasi-particle-like. Okay. So it's this hesitation of electrons between being delocalized and localized, which is really at the heart of the problem. So we actually know that on relatively short time scales or high energy in those systems, there are excitations that are best thought of in terms of atomic excitations. And the way we know this is using photoemission spectroscopy that has already been described in a few lectures in this conference by Atsushi or by Didi Sama. We see this, for example, if we take a Mott insulator, that DC3MTiO3, which LDA would get to be metallic, of course, we see in the excitation, the spectroscopy of this. This is just angular integrated photoemission spectroscopy. Goes back to a very nice paper of Atsushi 2 decades ago. We see that, of course, there is a gap near the Fermi level because this is an insulator, but here about minus 1.5 eV, there is a transition, there is a peak, and this peak is best understood as a transition between the D shell of titanium in its ground state, which is occupied by one electron, to the empty state D0. So you see that what this is, this so-called lower Hubbard band, is really should not really be called a band. It's really an atomic transition, which is broadened by the solid state environment. So this is how you should think of Hubbard bands, as broadened atomic transitions. Okay. It's very important, and you will see this later in the talk when I come to Hund's metals. It's actually very, very important to get the energetics of these transitions correctly in order to describe, to assess whether a material is a multi-insulator or whether it's a metal. So it's very important that we do a good job describing the energetic of the isolated atom with all the correct multiplets, energy of the multiplets, which are the ground states of an isolated atom, if we want to describe properly the energetics of the Mott phenomenon. And this is one of the problems with band structure calculation methods, since they don't start with atoms, they don't have the energetics of the multiplets right. And this becomes even more severe when we go to F-electron systems, where the multiplet structure is really very important. You'll see this coming back when I describe the Hund's metals. Okay, so you could think that these atomic transitions are only important in the case of insulators, but actually, when you go to metals, to correlated metals, even relatively moderately correlated ones, these two-time scales, quasi-particles at low energy, atomic-like excitations at high energy, is something that you still see in the photoemission spectrum of correlated metal. And again, the paper of Atsushi of 1992 demonstrated that very, very clearly. Here is a more recent higher photon energy photoemission paper on this, let's say, Drosophila of the field, you know, this metal which is not doing too much, but which is a good test case. You see here that we have quasi-particle excitations with a bandwidth reduction by about a factor of 2, but we have this lower Hubbard band here, which is present even in the metallic state. So we need to cross over from a high energy description with all the multiplets correctly included to a low energy description with a wave-like, where a wave-like description of quasi-particle excitations will work. Okay. So that's basically summarizing what I just said about the need for a description of solids that goes back to the atoms, basically. Okay, so this is one way, at least, perhaps a more modern way, to view dynamical mean field theory. This is exactly what dynamical mean field theory aims at doing. It was perhaps not presented exactly like this 20 years ago when these methods were invented, but this is the way I now like to present this sort of approach. So what is the basic idea? And I will just give again a cartoon picture of this. And on Tuesday morning, where there will be a school lecture, I'll do it on the blackboard. I will give a more detailed presentation of the basic equations and so on, following using some of the tools that Vijay introduced in his lecture. So the basic idea, I guess all of you now are more or less familiar with this. We have a solid, we have atoms which exchange electrons through the tunnel effect, and we replace this problem by one atom. So we are going to treat this atom the best we can, describing hopefully all the multiplet states of this atom. Usually when we do that for a real system, what I'm saying here is a little bit of a cheat because we do that only for a subshell of the atom. We cannot really handle all the states, but we do our best. And this atom can exchange electrons with an effective medium. And the effective medium is, of course, there to represent the rest of the system. So there will be a self-consistency condition that couples these two entities, the atom and the effective medium. So the basic equations of dynamical mean field theory are basically made of two parts. One part describes the physics of this atom coupled to an effective medium, and the other equation is a self-consistency condition which relates these electron exchange processes to what's going on the other side in the lattice. So you can view it pictorially in the following way. Let's go back to the Hubbard model just to use our favorite toy model. You can think of the Hubbard model as a bunch of atoms, very simple one-level atoms, localized on each lattice site. Each of these atoms can be in 4 possible configurations. It's really the simplest possible description of a correlated atom, either no electron, electron spin up or spin down, or doubly occupied. There we have to pay a price U. And what the local problem describes is the sequence of quantum fluctuations, the history of the quantum fluctuations between these 4 atomic sites as time evolves. So as time evolves, our atom may start in state 0, then switch to state up, then to doubly occupied, and so on, by exchanging electrons with the reservoir, okay? And this is the first equation of dynamical mean field theory, namely writing an energetics, or more precisely an action, which describes these processes. So in technical terms, and the students here have already been exposed by Vijay to this sort of thing, in technical terms, we write an effective action for this atom. If we had an isolated atom, our effective action would just look like this. You would have a D level, which is the position of this single particle level, plus an interaction term, and this provokes switches between the different configurations. And then we add to this isolated atom action, we add a term that we call a hybridization term, which describes, as you see here, the process of destroying an electron at time tau on the atom and putting another electron with the same spin at another time tau prime. The amplitude delta for doing this, which is a function of time or a function of energy or frequency, is really a generalization to the quantum world of the Weiss field of usual mean field theory. So this is important to keep this in mind. This object is really the one that should be called the dynamical mean field or the quantum Weiss field. Okay, indeed, if you maybe I should switch to this slide, you can make a comparison between the conceptual foundations of different types of mean field approaches, and you will see a very great similarity between these different theories. For example, if you take the standard mean field theory of a magnet, we need to define a local observable. Our local observable is the local magnetization. We need to decide how we are going to represent this local observable, and in the case of classical mean field, we have a spin in an effective field, which is the Weiss field. And then we have a self-consistency condition, which relates this Weiss field, H, to the local magnetizations. That's the equation that H is the exchange times the sum of all neighbors of the magnetization on the neighbors. Okay, so we have all these ingredients of a local problem, a self-consistency condition, the definition of a local observable, and so on. So DFT also does something like this. We have a local observable, which is the local electronic density. We have a representative system, which is the Kohn-Sham problem of electrons in an effective potential. The effective potential plays here the role, the Kohn-Sham potential plays here the role of the Weiss field in the context of DFT. It's a function of position, but again, it's not a function of energy or time. So you see these two theories, one for homogeneous system, one for a system that would have a spatial dependent local density, share in common the fact that in both cases, the Weiss field is a static object. What DMFT does is that it picks as an observable a quantity which is the local Green's function, which is a full function of energy. And as a consequence, the Weiss field is also a function of energy or time scale. And this is hence the name dynamical. And this is really what we want, because we want to describe how the nature of the excitations change as we go from short time scale high energy to low energy long time scale. Hence, the omega dependence of this Weiss field is absolutely crucial. Okay, so this is Mr. Pierre Weiss and a bunch of very famous people meeting at Paul Ehrenfest's house in Leiden quite a while ago. And so here we have the generalization of the Weiss field. Okay, so I have described this effective action description of the local problem. What I have to do now is to describe the self-consistency. And this self-consistency is really a statement about the self-energy of the problem. So here comes the approximation. We're going to approximate the full self-energy associated with the one particle Green's function of the full solid, which is usually a function of energy and momentum, by something which is only a function of energy. And of course, you see that this will be perhaps okay when the spatial correlations are reasonably short range. If the spatial correlations become longer range, this approximation will become worse and worse, and I'll come back to this later. So provided we make this approximation, we can then identify this self-energy with that of our local embedded atom, which we call a quantum impurity problem. And this is just enough to close the loop, because now we can just say that the local Green's function in the lattice should coincide with the local Green's function of the impurity model, which has its own self-energy, and when you turn the crank, you can write this self-consistency condition in this manner. Okay? So so what you have to do is start from a dynamical Weiss field that you don't know, because this is a self-consistent thing, solve this effective quantum impurity problem, obtain a local Green's function, obtain a new value of your updated value of your Weiss field using this equation, and iterate that process until it converges. So that's the DMFT loop. This is the self-consistency condition here, and this is solving this quantum impurity problem, which is, of course, the most difficult part in this enterprise. Okay, so you could say, okay, why do I know that this theory has anything to do with reality? Why should it be useful? And you can give a few arguments in favor of, which lead you to the optimistic view that indeed it may be useful for something. So the first observation is that this theory by construction is going to be okay, in fact exact, for the non-interacting system. Because the non-interacting system has no self-energy. The only assumption we made is that the self-energy is local. Nothing is more local than zero. It's the same at all k point. It's zero. So by construction, this is exact. Okay. So you see, nevertheless, that we've done something a little bit perverse when it comes to the non-interacting system. We have represented the local Green's function of a free band by that of an embedded level in an effective bath with which it exchanges electrons. And it's really nice that this can be done, but somehow this is not the most natural limit for this theory. The most natural limit is that of the isolated atom. In the isolated atom, of course, we are also exact when there is no hopping, because the atoms cannot communicate, and so, of course, the self-energy is then local spatially. So we have achieved a goal, which is that whatever we do in between, which may be crap, we nevertheless interpolate between the small u and the large u limit. So we have something which is, or between, say, the isolated atom and the band limit. Okay, so that's already very reassuring. Then for people who are more formally oriented, you can actually show that these equations become exact in the formal limit that was introduced in 1989 by Metzner and Volhart, which is the limit of large dimensionality or large lattice connectivity. I will come back to this on Tuesday in the pedagogical lecture. Okay, so we have a theory which is exact in both limits, strong coupling and weak coupling if you want, and which is also exact in some mathematical limit of large dimensionality. And this is not a curiosity, this is actually a very useful mathematical limit to have in order to make sure that what you are doing is meaningful from the point of view of some rules and everything. And also, physically, it's very logical that this becomes exact in this limit, because it is in this limit that the spatial correlations become shorter and shorter range. This is actually the case of most of mean field theories introduced in statistical mechanics, like the Weiss mean field theory. Okay. So now, what I want to spend a few minutes doing is to describe what we have to do to solve the tough part of this problem, which is solving this effective quantum impurity problem or embedded atom. So what we have to do is we have to use numerical techniques. So in contrast to simple mean field in classical StatMech, this approach does not lend itself, except in very special cases, to full analytical solution. We have to use some numerics. Okay? The good news is that in simplest cases, at least, for example, in the case of the single orbital, single band Hubbard model, the effective quantum impurity problem that we have to solve is, for example, devoid of any minus sign problem when we solve it with Quantum Monte Carlo methods. There are also, the other piece of good news is that there are many other algorithms than Quantum Monte Carlos to solve this kind of problem, and there is a long history of developing powerful algorithms like the NRG, on which Thomas will give lectures next week, for systems that do not have a too large Hilbert space. So to a certain extent, we have realized at least a modest part of the program of Paul Dirac that I mentioned yesterday, which is that we have indeed developed some approximate practical methods to attack this problem, because these problems can be solved on the computer. Okay. Now, the thing I want to emphasize, and this brings us in more recent history, that there's been tremendous progress, actually remarkable progress, in pushing the DMFT into a new age, thanks to the development of beautiful algorithms in recent years. And we have in this room several of the people who have been responsible or guilty for this, namely Philipp Werner, who must be somewhere here, and Andy Millis, whom I definitely see here. What these people have done, starting also with the work of Alexei Rubtsov, who is not here, is to develop continuous time Monte Carlo methods, both, so I'm not going to enter into technicalities because you are going to have lectures next week about this by Philippe and Michel Ferrero, both from an interaction expansion point of view or from a hybridization expansion point of view in the Weiss field delta. And I think it is fair to say that these breakthroughs have actually allowed us to solve the DMFT equations in regimes in which it was unthinkable only 10 years ago to solve them, especially going to very low temperature and handling more realistic atomic shells. So this has been an extremely important development in the field. Just to give you an example, when we combine the DMFT with realistic electronic structure method, 10 years ago, we could study a standard oxide at a temperature of about 1,000 Kelvin, perhaps. Now we can study, I'll show this to you later, an oxide like strontium 2 ruthenium 04 using fully realistic LDA plus DMFT at 20 Kelvin. So this has changed the landscape completely. Okay, so because of these sophisticated algorithms and efficient algorithms, there is also a certain need for efficient sharing of computer codes. And I just want to emphasize some of the work in this direction, in particular, the work in the group of Olivier Parcolin, in our group in Palaiseau, which is this TRIX library toolbox for research on interacting quantum system, which really have Olivier and Michel as master architects, and you will be exposed to this in the second week of the lectures. Okay, so this is it for the introduction to the method. What I want to do now is switch gear a little bit and give you a notion of some of the recent things that have been done. Before I talk about recent things, I will start with something which is not recent, which is actually very old, which has 15 to 20 years, which is really an early success of DMFT. One of the early success of DMFT for models has been to provide a fairly complete and detailed theory of the Mott transition, which turns out to put together many of the previous concepts like the Brinkman-Rice or the Mott-Hubbard transition in this field into a single unified framework. And again, I'll talk a bit more about this in the pedagogical lecture on Tuesday. You've seen this plot before by other speakers. Basically, what the Mott transition description, what the DMFT description of the Mott transition is, can be summarized here. You start from, say, a half-field band. This is occupied, this is empty. You crank up the interaction, and you see gradually the separation into two kinds of excitations. Low-energy excitations that correspond to quasi-particles that have a reduced bandwidth. This is the Brinkman-Rice phenomena. Quasi-particles acquire larger effective mass. And the formation, the transfer of spectral weight to lower and upper Hubbard bands, which are really atomic-like excitations. So you see that both types of excitations are present in this theory, and it offers the possibility of describing the transfers of spectral weight between the two kinds of excitations. At some point, there is a transition. These quasi-particles go away, and we are left with a system that has a Mott Hubbard gap and is a Mott insulator. The detailed story is actually a little bit more complicated than this. The generic phase diagram for the Hubbard model at half filling using DMFT is something like this. This is just a cartoon. At high temperature, it has a crossover between a metal and an insulator with local moments. If you go to very low temperature, you eventually discover a critical point, which is at finite temperature, which is something like a liquid-gas transition. The liquid should be thought of here as the metal that has many double occupancies. The gas should be thought of as the insulator that has very few double occupancies. There is a first-order transition line in this phase diagram. Eventually, this first-order transition line reaches a quantum critical point, which corresponds to the Brinkman-Rice quantum critical point. But usually, in most systems, this is masked by magnetic ordering, which, of course, has to be there because the system has a local moment, or something must happen, either magnetic ordering or some sort of entangled spin liquid state. Okay, so how do we decide if we are in the metal or the Mott insulator? Again, the key thing here is the Weiss field. We have to look at the Weiss field. If the Weiss field is finite, has more precisely a density of states, which is finite at low frequency, then basically our local moment of our isolated atom is going to be screened. This is called the Kondo effect. And this is the local description of the metallic state with DMFT. If, on the other hand, delta of omega is gapped, there are no low energy states to screen this local moment. And as a result, there is no Kondo effect, and the system self-consistently sustains a finite gap and is an insulator. Okay, so just in a nutshell, elaborating on this early success of DMFT, you see that this theory has both quasi-particle excitations, atomic-like excitation. It can describe the gradual transfer of spectral weight between these two features as we crank up the interaction or as we change another parameter like temperature or whatever. Okay, so now I would like to show you something which elaborates further on the talk of Michel Ferrero yesterday, which is something, as emphasized by TVR yesterday, that could have been done many, many years ago, but was not fully done, and which is a direct continuation in some sense of the study of the Mott transition or of strongly correlated metals, starting with a single band description. So here we had a talk from Michel in which he explained how this theory can account for the gradual crossover from a low temperature semi-liquid metal, which is this region here, to a very high temperature bad metal in which the resistivity is larger than the Mott-Feregel limit that he described yesterday. And the point is that, in fact, there is a rather extended region in this phase diagram, which here is temperature versus doping, but could apply to many other systems and material, in which we have a metal with quasi-particles that are still present in an operational sense, in the sense that if you do photoemission spectroscopy, you will find a quasi-particle peak. But the lifetime of these quasi-particles is shorter than the one that you would predict using the Landau argument at low energy. So it's no longer omega squared. Okay? So we call these resilient quasi-particles to emphasize that the quasi-particle concept invented by Landau is in fact much more robust than the specific prediction of Landau theory for the lifetime of these quasi-particles at very low energy. And the existence of quasi-particle extends at much higher energy and temperature scales than the strict Fermi-liquid regime where T-square behavior is observed. Okay. So yesterday, Michel showed this optical conductivity curve, which shows you three regimes. This regime of Landau theory where there is a Drude peak, and there is something here, and then there is a mid-infrared region which corresponds to the transition from lower Hubbard band to the quasi-particles. Then this intermediate region where there is still something like a low-frequency peak, which is not quite Drude, and then there has been transfer of spectral weight between this and the mid-infrared region, and then when we reach Mott-Feregel, then all hell breaks loose. There is transfer of spectral weight all over the place, implying energy scales of order U, and the system is really broad and featureless. So here, I want to attract your attention to this here. Obviously, this, you might believe me if I tell you this can be fit by 1 over omega squared or the form, but this obviously is different. This is a foot, which is not obviously of the Drude form. So what is this? Well, the point is that this is actually the signature of Landau-Fermi liquid theory in optics. If you think of Landau-Fermi liquid theory, the optical scattering rate, 1 over tau optical, is t squared plus some coefficient times omega squared. As long as the t squared term dominates, we can view tau as being a constant, and we have a Drude form. This is this region. But when we become sensitive to the omega dependence of the optical scattering rate, we deviate from Drude form, and we have this foot here. So the signature of Landau-Fermi liquid theory in optics is a deviation from the standard Drude form, which is something which is not so often emphasized. Usually people say Drude is Fermi liquid. Well, actually, if you really want to see Fermi liquid in optics, you should look for deviations from standard Drude form. And believe it or not, there hasn't been up to now, up to very recently, any experimental demonstration of this so clearly from optical spectroscopy. Okay, you can be a little bit more, I'll show you a breakthrough on this very recent one in the next slide. So you can be a little bit more specific and analyze the universal scaling form of the optical conductivity for a local Landau-Fermi liquid. And what you will find is that sigma of omega is really a scaling function of 2 variables, one which is h bar omega over kt, and one which is h bar omega over kt square, which is obviously the inelastic scattering rate of quasi-particles in Landau theory. So there are really 2 regimes. There is a regime where omega is much smaller than kt, in which here is a log-log plot of this function, which can be derived analytically. You can find the formula in this recent paper here. This is Drude form here, which corresponds to when this variable is very small. But when you actually go to h bar omegas of the order of kt, what we call the thermal regime, then you should see a hump here, which corresponds to the universal scaling in h bar omega over kt of this optical spectrum. And this hump here is the same as this foot there, just in a log-log representation. There is a very universal prediction, which is very old, which goes back to Soviet physicist Mr. Gurzy back in the 50s, which specifies the relative coefficient between the omega and the t terms in the optical scattering rate. And this relative coefficient should be 2 pi square, in the same way that in the single particle self-energy, this relative coefficient is pi square. And there's been a certain resurgence of interest recently in trying to assess from experiment whether this 2 pi can be really seen. Up to now, it was not possible. Very recently, there's been some beautiful experiments in Dirk van der Marel's group in Geneva on strontium-2 ruthenium-4 that have revealed this 2 pi factor. And this is a paper that, a joint paper with the Geneva group, which has been recently submitted, which is not yet on the net, so this is really very fresh stuff. I'm not sure I'm even allowed to show you that, but okay. Which shows you 3 things. So these are optical conductivity spectra for strontium-2 ruthenium-4 for 3 different temperatures. A low temperature in the Fermi liquid regime and a very high temperature somewhere in the resilient quasi-particle regime. These are the wiggly lines. These are the experimental data. What you see here in dashed is a comparison to the universal scaling functions of Fermi liquid theory that I showed you before. And what you see with the dots here is a realistic dynamical mean field calculation without any adjustable parameter of the optical spectroscopy for strontium-2 ruthenium-4. And so what you see here is that there is quite beautiful agreement for all temperature scales between the experimental values and the DMFT calculated values. The DMFT calculated values are, of course, not exactly on top of the experiment because impurity scattering is not in the theory while it's in the material. But I'll answer your question after I finish describing this. What you see here is that at low energy and low temperature, there is a beautiful agreement between the data, the universal scaling forms, and the DMFT, which also, of course, follows this universal Fermi liquid form. But there is a certain energy scale here, or temperature scale here, at which the universal Fermi liquid form, about 0.1 eV, at which the universal Fermi liquid form obviously doesn't work anymore. There is an excess conductivity in the data, and the realistic DMFT calculation does a beautiful job at capturing quantitatively this deviation from Fermi liquid theory in the experimental data. Tanushree, you had a question. Okay, so the wiggly lines, the noisy line like this are the experiments. The dashed line are the analytical expression corresponding to this universal Fermi liquid form, while the circles correspond to DMFT calculations. Oh, sorry. Yeah, good question. Imaginary and real part. Okay. Sorry about that. Blue is real part. Red is imaginary part. I should have said that. And it's all log-log. Okay. So now what I want to show you is that actually not only we can reproduce this quantitatively, but we can also understand what this is. And what I'm going to show you, or well, at least tell you, is that this actually does correspond to these resilient quasi-particle excitations, which are no longer Landau-like, but are still quasi-particles. You remember yesterday when Michel showed some of the self-energies in simple one-band model, a distinctive feature of the scattering rate was that it obeyed, so this is the imaginary part, it obeyed some omega square behavior here, but then at some scale, it started saturating with a very strong asymmetry between particle and holes. This is a realistic calculation, no longer one band, for strontium-2 ruthenium-4. And what you see here is actually quite the same thing. On the negative omega part, there is still a rather fast increase of the scattering rate. But on the positive omega part, there is even a turnaround. And this, in turn, reflects in the real part of the self-energy. There are kinks here, but then there is even a maximum of the self-energy. And so this means that at positive omega here, there are quasi-particle excitations that have not so large scattering rate and a dispersion, because the self-energy becomes smaller, a dispersion which is actually closer to the original band. And we can show by doing some model calculation, for example, that this feature at positive omega is actually responsible for this deviation from Fermi liquid theory in optics. So this comes with a very definite prediction, which is that quasi-particle states above the Fermi level in the dark side that was already emphasized by Silke and also by Michel in their talk, there should be excitations, and you can probably see this here. This is Fermi level. These are intense quasi-particles with renormalized bands. But here you have a band that extends to 0.5 eV or so, which corresponds to a dispersion which is even actually steeper than the bare band dispersion. And these are these resilient quasi-particles which are responsible for this deviation from Fermi liquid in optics. Okay. So how much time do I have? Like 20 minutes? Okay. So, fine. So I told you this story because I think it was an amusing story to tell. It takes its roots into very old stuff. You know, the Mott transition or the description of the correlated metal in single band from DMFT, old stuff from 20 years, 15 years ago, to very recent stuff. And as you see, some of that stuff could have been done indeed quite a few years ago using Thomas energy solvers, for example, but some of that could only be done recently. We can only study strontium-2 teniomorpho optics with that level of precision thanks to Philip and Andy's algorithms. Okay. So I have on the menu quite a few things now which give different direction of extensions of DMFT or things done with DMFT in recent years. I'm not going to be able to cover all of this in 20, 25 minutes, so I'm going to skip some of these things. So obviously, one of the big approximations that we had to do when constructing single-side dynamical mean field theory is assuming complete K independence. And this is okay as long as the range of spatial correlations is not too large. As we go down in temperature, or as we get closer to some quantum critical point, for example, or to some ordering, we will have some correlation lengths that become large. And obviously there, you have to go beyond dynamical mean field theory, single side. Okay? A prominent illustration of this is, of course, cuprates, where we know that at low doping, even when we have partially destroyed the quasi-particles, for example, in the antinodal underdoped region, we have a very strong J that binds the spin together. Okay? And so spatial correlations, at least on a short-range level, have to be included. So single-side DMFT has to be generalized, and this can be done by going to clusters. So going from a single atom mean field theory to a kind of molecular mean field theory. And again, there are several people in this room who have taken pioneering steps in this already many years ago, like Krish himself, who developed this dynamical cluster approximation to attack this sort of problems. Okay, so there is a whole line of research which is going beyond single-side DMFT to include momentum dependence and to describe how magnetic correlations affect quasi-particles in those regimes where single-side DMFT is no longer enough. I was planning to show you a few slides on this. I'm not going to do that because I'm running out of time, and André-Marie, I'm sure, will give some view on what this has taught us for cuprates. But at least one thing I want to say is that, in my opinion, and I believe also in the opinion of Andy and André-Marie, these methods have established, beyond any doubt, that the single-band Hubbard model has quite a few of the, at least qualitative physics of cuprate superconductors. In particular, it has a pseudo-gap at low doping on the whole dope side, and so on. Okay, so I'll skip this because I don't have too much time. Maybe I'll just show this just to illustrate what I was saying. This cartoon is extracted from a joint paper of Andy, myself, Emmanuel Gull, and Michel, and many others, in which we show that as a function of doping level, the whole dope Hubbard model has really three kinds of regime: a large doping regime in which we have a nearly isotropic Fermi liquid, in which single-side DMFT is more or less okay; an intermediate regime where there starts to be strong momentum differentiation between nodes and antinodes; and a low doping regime in which the antinodal states are really gapped out. And this allows us to describe the so-called Fermi arcs of cuprate superconductors. what I mean by sector selective is that if we look here in the Brillouin zone, okay, the way this cluster, so you know that these Fermi arcs appear, right? And the way this cluster dynamical mean field theory, at least in the DCA form, capture this phenomenon is to have this region of the Brillouin zone be still in an incompressible insulating state, while the sector close to the node is actually metallic light. So I mean momentum selective Mott transition. Okay. So in the 15 minutes that remain, what I will do is I will give you some, perhaps one illustration of something that has happened already about 10, 15 years ago, which has given considerable momentum to this field, which is a happy marriage, the marriage of DMFT with realistic electronic structure methods, DFT, DFT, LDA, and now GW, which you have been exposed to in the first week of these lectures. So this has been really an interdisciplinary effort that has brought together the community of DMFT and many-body people with that of the electronic structure calculation community. This started in the mid-90s, and the aim is really now to bridge the gap between the Hubbard model, which is kind of a spherical cow model of a solid, with something realistic for a true oxide like this. Okay. So real materials raise many fascinating puzzles. There is a very complex interplay between structural aspects, orbital degrees of freedom, and so on. And many of these materials have specific functionalities, as I described in the first lecture. We need material realistic techniques to actually be able to understand the physics of such systems, well beyond the simple Hubbard model. Models are, of course, very useful to understand qualitatively the main effects, but we need to be able to bridge the gap with real materials. So this is what realistic electronic structure DMFT has been achieving, and I'm going to give you a few examples. Are you going to talk, Andy, about distorted oxides and the effect? Yeah. Briefly. Okay, so maybe I'll skip this. That's probably better because I'm not going to have enough time to describe it. Okay, so I have different puzzles. So let me give you one here, which will connect more directly to the talk of Atsushi yesterday. This is a puzzle that you may want to raise when you look at transition metal oxides in general. If you look at the 3D series, transition metal oxides of the 3D series of transition metals, you will observe that these oxides are really dominated by the phenomenon of the Mott transition. And let me show you this. Here, there is a famous map, which is due to Atsushi, which beautifully emphasizes this. If we look here as a function of filling of the D shell and degree of correlation, we see that all the materials on this map that are in the gray shaded region are insulators. All the materials here are metals. So you see that the Mott transition is really a key phenomenon to understand the physics of these systems. However, when it comes to 4D oxide, the puzzle is that we see materials like strontium 2 ruthenium 4 that I already mentioned before, which are very correlated metals and nevertheless are not close in any obvious way to a Mott transition. It takes an enormous change in the structure to actually bring this series of material to the insulating side. You can do it by going to calcium 2 ruthenium 4 for reasons that I maybe explain later. But by and large, this class of materials, the ruthenates, is not close to a Mott transition. So the question is, why are the transition metal oxides of the 4D series, which you might expect to be weakly correlated because the 4D orbitals are so extended, still able to display strong correlation phenomena? A beautiful example of this is strontium-2 ruthenium-4. Strontium-2 ruthenium-4 is a very simple oxide. It has 3 bands of the T2G subset, XY, XZ, YZ. What you see here is that because XY is in the plane, it has a bandwidth which is fairly large of about 4 eV, almost 4 eV. And the effective U for this 4D oxide is not expected to be much larger than 2.5 eV. So why the hell would this material be strongly correlated? More strikingly, a strange paradox is that it is actually the effective mass of the broadest band, of the XY band, which is the largest, which has a factor of 5 enhancement, while the effective mass of the XZ and YZ band is only enhanced by a factor of 3 or so. Okay, so the answer to this question, we believe, is the following, is that there is not only U in life, there is also J, where J is the Hund's rule coupling. So that's the take-home message. In our opinion, and this is backed up by realistic LDA plus DMFT calculations, the 4D transition metal oxides are really correlated because of the Hund's coupling. This has been a quite instructive and interesting saga that has been going on over a few years now, which started with 2 pioneering papers, the paper of Philip, Andy, and others in 2008, and the paper of Christian Howley and Gabi Kotliar, which emphasized the importance of the Hund's coupling, and then our work with Jana Mravlier and Luca De Medici, both on strontium ruthenate and on putting this in a broad perspective for 4D oxides. For people who are interested in the details of that, you can look at a recent review article that we wrote with Jana and Luca in Annual Reviews of Condensed Matter Physics. So the short story about this, I could give a whole talk about this Hund's metal business, but the short story is the following, and you've already seen this plot in Atsushi's talk. If you actually look to a T2G shell with 2 electrons, or a T2G shell with 4 electrons, which is the case of ruthenates, and you calculate using DMFT methods the quasi-particle weight as a function of U for different values of the Hund's coupling, what you will see is the following thing. If there is no Hund's coupling, Z versus U has a Mott transition like this, very much like in the 1D Hubbard model. As you increase J, what actually happens is that the critical value for the Mott transition is pushed, in this case, to much larger values. And the effect of J on the Mott transition has been studied by many authors, mostly in half-fill shell, but not so often in shells away from half-filling. And the two situations are very different. At half-filling, for a half-fill shell, Thomas studied that many years ago. For a half-fill shell, as you increase J, the critical U goes down. For a non-half-fill shell, is the opposite. As you increase J, the critical U goes up. And you can understand that very, very simply from the energetics of the atomic multiplets. Hence the importance of having the energetics of the multiplets correctly. So there is this effect that if you just look at this, you would say, okay, J is going to decorrelate my system because it's actually driving the system away from the Mott transition. And that already raises a bell. You know, maybe this is why, indeed, these systems where U is smaller, the 4D transition metals, are far from the Mott transition because U critical is so large. On the other hand, what you see here, which is truly remarkable, which is that in the metallic phase, here, as you increase J, the quasi-particle weight goes down as you increase J. So this is exactly the opposite effect. Despite the fact that you are driven away from the Mott transition, increasing J makes the metal more correlated. This is what we call Hund's metals. Metals in which the small value of z is really due to the Hund's coupling. Okay, so you can say that the Hund's coupling really has two phases for these partially filled shells. One phase decorrelates the system by pushing the Mott transition away, and the other phase makes the metal more correlated. This is why in this paper here, we call this Janus-phased influence of Hund's rule coupling. Some of the people thought that Janus is a physicist. He's actually not a physicist. He's a Roman god with two faces, but he was promoted to being a physicist already well before us by Pierre-Gilles de Gennes in the context of soft condensed matter. Of course, this is all small players, you know, because in India you have gods with many more faces. And I'm sorry, I already made that joke in TVR's birthday conference 2 years ago, but I can't resist to do it again. Okay, so this has very important consequences. In fact, if you ignore the Hund's coupling, you would conclude that the critical U is largest for a half-filled shell. This is the phase diagram, U versus filling of the shell, and you see that for j equals 0, the largest critical U is for a half-filled shell. On the other hand, when you turn on j, it's exactly the opposite. The smallest critical U is for a half-filled shell. And so you go from something like this to something like this. And as you saw from Atsushi's map, this behavior is actually what is found in nature, not this one. Okay, so with this in mind, and assisted by LDA plus DMFT calculations for many different materials, you can sort of draw a map. And this will probably be one of my last slides, in which you put here the filling of the T2G shell, and here U over D, and some fixed value of the J over U ratio for the Hund's coupling. What you see here are the black bars are the Mott insulators, and the intensity of the color elsewhere is related to the degree of correlations. A light color indicates very strongly correlated metals, and a dark color, weakly correlated metals. And what you see here is that if you have a half-filled shell, you only find strong correlated metal very close to the Mott transition. But if you have a non-half-filled shell, especially 2 electrons or 4 electrons like in rutinates, you have a very wide region of very strongly correlated metal, even though you are not far from the Mott transition. So not close to the Mott transition. So this is the case of the rutinates, which we estimate to be somewhere here, far from the Mott transition, but still strongly correlated. This is what we call the Hund's metals. The specific aspects of the half-filled shell have importance to understand why some oxides, like the technetium oxides, for example, which are nasty radioactive beasts, have so high Néel temperature, and Marcus Eichhorn will give a talk on this later today. Is it today? Yes. Okay. So I was also planning to tell you more about the direction that I mentioned yesterday in the general lecture, namely the possibility of controlling electronic properties of these materials via selective excitations using light beams. But I obviously don't really have time to do that, so I'll be happy to either sneak a part of this in the third lecture or discuss it in private. So I'll skip this just to give you a few conclusions. So what's next? Well, first of all, I should say that there are, of course, many, many things that have been offsprings of DMFT that I didn't have time to describe here. Again, I took just a few examples related to my own work, but there are many other things that you will discover through talks in this conference. But we also have challenges ahead of us. So what are these challenges? First of all, it's clear that we need advance on the question of momentum dependence. There's been beautiful work done in the past 10, 15 years using cluster extensions. We'll hear more on that from André Marie. My view on this, and I don't know if Andy and André Marie share this view, is that cluster extensions of DMFT have done a lot of what they can do, and now we need other techniques. There are possible promising routes for doing this. which is using DMFT in combination with lattice diagrammatic Monte Carlo. And this is something which is quite interesting to explore. There are also important directions on the front of real materials. One of the things which is dear to my heart, but I haven't worked on myself in the last few years, which is to just try to get rid of LDA, of DFT LDA. DFT LDA is such a nice theory that it's hard to get rid of. On the other hand, it's not diagrammatically based. It's not using the Green's function as a basis object. So it's a pain in the neck in trying to marry it with many-body methods. You've heard talks by Zielke and Ferdi, and probably Philip will talk about this, trying to overcome this and use GW instead of DFT LDA. There is also other very interesting directions, like non-equilibrium. This is what Philip will talk about, I think, or using DMFT in new areas, like, for example, molecules. There are some biomolecules that have transition metal centers, like enzymes, for which the DMFT construction seems to be quite appropriate to treat correlations on these specific centers. And Cédric Weber will talk about this.
To be not so easy to find in literature. And then in this heavy fermion thing, it seems to Drude works very well. So
yeah.
Where should be this second half?
Okay, so I'm very, very familiar with the paper of Martin on this heavy fermion compound. And what Martin showed is that the standard Drude form fitted his data quite well. But when you actually look at the data, there is a window of frequency which was not explored. And this is precisely the window where you would expect this Fermi liquid food to be.
Okay, yeah, I guess
so
technically it's a bit hard to get this
well, yeah, you have to find a material in which the Fermi liquid scale is such that you can have the right bolometers to access the right energy range. And this is what was done by the Geneva group on strontium 2. But I expect this to be very general. So Fermi liquid theory is deviation from Drude form. This is not a big news. I mean, it was known before. But what's nice is actually to see this in an optical experiment, and especially to see this also with the right 2 pi factor, which various people have tried to find recently.
So I'm sorry, can I just, on precisely this point, Timisk in particular has been publishing papers which say that it's not 2 pi. And you're saying that he's getting mixed up with crossover? Or?
Yeah, exactly. Well, I mean, Timisk is well aware of the fact that it should be 2 pi.
I understand that, but his point experimentally was that the data doesn't look like 2 pi.
Well,
and your interpretation is that that is because...
Well, I mean, the data that would reveal the 2 pi was not available up to now. And now 2 pi has finally been revealed, I think.
So maybe going back to Martin Dressel's experiments on all these organic charge transfer salts, he's now really going into this regime by using terahertz techniques.
Yes.
So
this will also come in these systems, I'm
right.
sure.
So
in fact, Martin in organics, on this system was the closest to actually get this Fermi liquid factor close to the appropriate value.
So I think that there is a lot of hope in getting this material.
So we're going to have a focus session at the IISc conference, which happens to be in France this summer, on this. And all these guys will speak there. Martin,
I mean, we try to do this optical conductivity, but in our calculations, we don't go so low in temperature. So that's why this regime is very difficult, as you say.
Yeah.
I mean, with the LDA plus the MFT, and calculate the optical conductivity, but you need to go to very low temperatures.
Yes, actually, since you are asking this question, yeah, that's completely correct, I agree. And since you're asking this question, I just want to show you one slide that I skipped. Well, maybe it would be easier to jump at it like this. Just to show how remarkable here. The new solvers that have been developed over the last few years can now allow to address this problem. What you see here is the same optical conductivity plot that was shown here, obtained by a combination of CTQMC and PAD to handle the low frequency part because of the problems that Thomas mentioned, which is that energy at very, very low frequency runs into accuracy problems on the self-energy, and energy at higher frequency, where PAD continuations of Monte Carlo doesn't work so well. So we combine these two techniques, and what you obtain when you plot in log-log form these optical conductivity spectra are these things here, the plane lines. And this is a comparison between these calculations and the universal Fermi liquid form that was derived in this paper with Berthaud and company. And you see how remarkable this comparison is. So these solvers have really changed our life.
They have.
In your phase diagram, I see you have strontium ruthenium oxide, where you have this
The
Hund's
blue,
rule.
the blue period
The blue
painting.
thing.
Okay. Let me try to
But the
dig
strontium
this.
ruthenium oxide is the only 4D compound which has a ferromagnetic ground state. Barium ruthenium oxide has, but that's at high pressure.
So this guy, the 214, does not have a ferromagnetic,
But
this
113,
guy, yes,
it's a ferromagnet.
yes,
And if you go to calcium, it's not anymore a ferromagnetic
Correct.
ordering.
yes.
So can you explain all that?
Okay, that's an excellent question, and I'm not going to explain it now, but what I want to say is that we are well aware of this issue, and Andy and I have an ongoing collaboration, and Jernheim Ravlier and so on this issue, and we'll soon have a paper, I think, where we can explain this difference when we get together to work rather than travel in India. Yeah, I mean, this can be explained, we believe. It's has to do with distortions.
Okay, so when you showed actually the, the spectral function, the plot, actually it has a three-peak-like structure.
That's kind of a universal cartoon in this field. You mean three-peak structure, lower Hubbard band, upper Hubbard band,
Yes, and the
quasi-particle? Yes?
quasi-particle. And something similar to that, at least I have seen something called below this Kondo temperature, there
Yes.
is something Kondo resonance, and that has such actually.
Sure.
So is there something, these are related? Or?
Absolutely related. So you're asking about this, right? Let me make sure I understand your question. You're asking about this, no? This is just a cartoon. You'll see many real calculations later in the week, but you're asking about this. Yeah. Okay. Yes, the reason why this has a three-peak structure is the same reason why in the Kondo context or Anderson impurity context, the spectral function has a three-peak structure. Okay? So what is this? This is the process by which you remove an electron from the d level. This is the process by which you add an electron to the d level. In the solid state, this is called lower and upper Hubbard band. And these are the quasi-particle states which come from the fact that your local moment is screened by the other conduction electrons. And this gives rise to the Abrikosov-Soule resonance. So within the MFT, the description of a Kondo, the description of a correlated metal is that of a self-consistent Kondo screening of the local moment.
But so here actually is that, the calculations you are doing mentioned something like it's high temperature, at large temperatures, but the Kondo temperature scale is very small. So,
No, the Kondo temperature scale in this context is the width of this peak, essentially. So the difference between a single impurity Anderson model in a fixed in bath and the self-consistent DMFT context is that in the impurity, in the magnetic impurity context, the Kondo scale is exponentially small at large U, right? While here, because we are doing the Kondo screening with the same states that participate in the resonance, that Kondo scale stabilizes to a value which is essentially bandwidth times Z. So below the transition, it has been boosted up, and above the transition, it's just zero. So the self-consistency aspect is extremely important. But I'll talk about this more in the school on Tuesday, and there will be more talks on that.
Yeah, almost the same question as Tanusuri, but let me put it in this way.
So you want the blue period plot again?
The strontium ruthenate story.
Strontium ruthenate,
Yeah,
yes.
I believe that this is a Hund metal, but it is a ferromagnet, so that.
So you are talking again about 113.
113, yeah.
Yes,
And,
yes.
it is ferromagnet.
Everything I
means-
said in this talk is about 214. Let's just be clear about this, okay?
But you put it in the
But here
phase
I've put,
diagram and
here I've put
this is
113.
ferromagnet means Hund's fluctuation is suppressed.
Yes, yes. So perhaps
still
you
it
should
is,
view
Hund
this. Yeah, so perhaps you should view this as describing 113 above the Curie temperature. Below the Curie temperature, there is a certain cutoff of correlations because those
specific
things are-
heat is enhanced already below TC, below Curie temperature. Yeah, so I'm a bit confused.
Yeah, no, please do, please. You've thought more about 113 than me, so.
Just a brief statement. There's a, let's say, a smooth crossover as a function of model parameters. If you have a compound with the appropriate structural distortions, blah, 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 such that it would like to become ferromagnetic in its ground state, right? You may then, as you change model, well, let me put it this way. As you change model parameters, you may go from a system which is a Hund's metal in its ground state, meaning paramagnet, large mass enhancement because of the Hund's coupling. Right, then as you change parameters, you cross over into the ferromagnetic phase. So there will be a ferromagnetic to paramagnetic quantum critical point in the model as you change something or other. The mass is largest at that critical point. In fact, I believe it diverges. And then as you go deeper into the ferromagnetic phase, the mass gradually decreases. So then I think I understand your question as a quantitative one. If you go to the fully polarized ferromagnet, very deep in the phase, then the mass enhancement becomes relatively small, just described by a Hubbard model. And as you get closer to the quantum critical point, it becomes larger again. So I interpret your question as a quantitative statement. How close is the 113 strontium ruthenate to this ferromagnetic critical point? And is there a consistent theoretical calculation which reproduces both the magnetic moment, which is, I forget, a half, a 2/3, 1 Bohr magneton something, and the mass enhancement? And I believe the answer is yes. But
yeah, and obviously 113 calcium is on one side and 113 strontium is on the other.
But they're both relatively close to this critical
Yes,
point. So
they're
there's
both
some
close.
Hund's metal fluctuations remaining, even though it's in the ferromagnetic phase. And if you were able to do something to push it farther into the ferromagnetic phase, the mass would decrease.
Yeah, and you would get a less correlated metal.
Please comment something on handling disorder system with DMFT, or what are the limitations of DMFT?
That's a good question. Okay, so you can use these methods to treat problems in which you have both local interactions and disorder. However, if you are really interested in systems that have an Anderson metal insulator transition between a disorder-induced localization and a metallic phase, you should be careful to actually treat the finite dimensional disordered problem as such. So you don't want to get too much inspiration from the large D limit because there is no Anderson localization in infinite dimensions. There are too many neighbors to hop. What you need to do is to diagonalize your disordered problem on the finite dimensional lattice and use the DMFT methods on top of that to treat local correlations. And there is a whole literature on this. The key names there are Vlad Dobosavljevic and Merino, and they have a couple of review papers on handling this disordered problem either with slave bosons or DMFT. So that's the problem of local moments in phosphorus-doped silicon, for example.
Any other questions? If not, please join me in thanking Antoine once more.